in number one, we want to find where f of x is concave up and concave down and find the inflection points. So what we're going to do is we want to do a plus-minus analysis on the second derivative. Okay, so for concavity and for inflection points, we use the second derivative. The inflection points might occur where the second derivative is 0. We have to do a second derivative test in order to determine that. So let's do that. Let's take the second derivative. Sorry, first we'll start with the first derivative, one step at a time. The first derivative, power rule, we have 4x cubed minus 24x squared plus 36x. We can factor out a 4 from this, so let's do that. X cubed minus 6x squared plus 9x. Okay, I didn't factor out x as well because it's easier to take the second derivative in this form. So now for the second derivative, using the power rule, we have 3x squared minus 12x plus 9. And we want to see where this is equal to 0. So let's factor out the 3. Factoring out 3, 4 times 3 is 12. And here we have x squared minus 4x plus 3. And this is equal to factored form x minus 3x minus 1. We want to see where this is 0. So this is 0 when x is equal to 3. And when x is equal to 1. So these are our potential inflection points, and we're going to put them on the number line. Let's now do our plus minus analysis. F double prime, that's 12x minus 3, x minus 1. On the number line, we're just going to put 1 and 3. And we see if we substitute in something to the right of 3, like 4, this is positive, so positive here. If we substitute in 2, we have negative, positive, so that would be negative. Substitute in 0 to the left of 1, and we have negative, negative, which is positive. So positive f double prime means concave up. I'll just indicate it like that. Negative means concave down, and positive means concave up. So here we have concavity changing, and our function is continuous at 1. And here concavity changing and continuous at 3, so that means that these are inflection points. So that would be 1, and this is f of 1. And this is 3f of 3. We substitute in this 1 back into the original function and this 3 here into the original function right here, and we get the y coordinates. Okay, so we have 1 comma 11 is an inflection point, and 3 comma 27 is an inflection point. In number 2, again, we need the second derivative in order to find where f of x is concave up, concave down, and inflection points. So let's start by taking the first derivative, and we need to, well, actually here we don't really need a quotient rule because we can write f of x in the following way. Let's write f of x like this. F is equal to x squared plus 1 to the minus 1, and so then we only need to do a chain rule here. Let's bring down the minus 1. X squared plus 1, subtract 1, and we have minus 2. And then by the chain rule, we have to multiply by 2x. Okay, so we have for the derivative minus 2x over x squared plus 1 squared. And now the second derivative, that's the one we need. Okay, we'll do a quotient rule there. Square this, and we have x squared plus 1 to the 4th. Bring this up, x squared plus 1 squared times the derivative of the numerator, that's minus 2. Subtract derivative of the denominator, so that would be 2. X squared plus 1 to the 1 times 2x times the numerator. Okay, what we're going to do at this point, we have x squared plus 1 in the first term and in the second term, so let's cancel x squared plus 1 from the numerator and denominator. Alright, so if we divide this denominator by x squared plus 1, we have x squared plus 1 cubed. And here divide by x squared plus 1, and we just are left with x squared plus 1 to the exponent 1. We have to do that throughout the whole numerator. So here we divide by x squared plus 1 as well. And that just eliminates that factor. Okay, let's rewrite this. Second derivative, so we have x squared plus 1 cubed in the denominator. In the numerator, we all multiply through by minus 2. And we have minus 2x squared, minus 2. And here we have a negative 2, a 2, and a negative 2. Multiply those together, and that gives us plus 8 times x squared. Let's simplify this. And we have 6x squared minus 2 over x squared plus 1 cubed. And we want to set this equal to 0 and solve. So we're going to set the numerator equal to 0. And we have 6x squared equal 2. X squared is equal to 2/6, or 1/3. So x is equal to plus or minus 1 over the square root of 3. So these are our potential inflection points, and now we're going to do the plus minus analysis on f double prime. So let's do that right here. So here we have f double prime. Okay, 6x squared minus 2 over x squared plus 1 cubed. Now notice the denominator is always positive, so we're going to just have to substitute into the numerator. Let's put these 2 points on the number line. 1 over square root 3 minus 1 over square root 3. If x is 1, for example, the numerator is positive, and remember the denominator is always positive. We substitute in 0, in the numerator we get minus 2, that's negative. We substitute in minus 1, we get positive. So the numerator, so the function f is concave up here, and here it's concave down, and here it's concave up. That means these are x values of inflection points. So we have to substitute back into the original function to get the y values. So let's just look at those inflection points. Okay, we'll substitute in a minute. Let's just remember what we're substituting into right here, into 1 over x squared plus 1. So this is 1 over 1/3 plus 1. 1/3 plus 1 is 1/3 plus 3/3, that's 4/3. So it's 1 over 4/3. This would be 3/4. And this is also 3/4. So these are inflection points.